In this video, we're continuing section 2.4, and we are going to focus on how we find the vertex and sketching parabolas. All right, so I want to get right into an example where I want to compare the graph of y equals x squared to the following functions. Okay, so there's a few examples I want to look at kind of all together. So in part A, I got the function f of x equals negative x squared, and then B, I got 2x squared. And then there's also these three examples I want to look at that start on the next page. Okay, so what I want to do is, let me draw some axes, just get myself ready here. I'll draw some axes for this one. So what I want to begin by doing is drawing the graph of the original thing, y equals x squared. So let's recall that y equals x squared, that's kind of like our basic parabola graph. It's an upward facing parabola, it's got its vertex at the origin, and it's kind of going upwards like this. So for all of these, I want to draw like my axes, I want to draw the graph of y equals x squared, just like I did. And then for each one, I want to draw also, maybe in a different color, this other function. So like for part A, I want to draw the graph of f of x equals negative x squared. Okay, so what does that negative do to the graph? Well, it's going to reflect the graph across the x-axis. So when I flip it across the x-axis, now my parabola is downward facing. Okay, so this is the graph of y equals negative x squared. So this reflects, putting a negative in front of the formula, it reflects it across the x-axis. Okay, so at this point what I want to do is I want to give you an opportunity to try each of these other ones. For each of these other ones, draw the graph of y equals x squared, and then try to draw the graph of this other function that's given. Okay, so pause the video for about maybe 2 minutes to try this. 4, 3, 2, 1, pause it for about 2 minutes to try these. All right, and while you're doing that, I'm just gonna get ready and draw in some axes. But you are pausing the video and you are trying these. All right, so hopefully you did that. Hopefully you paused the video to try these. If not, definitely do that. The pauses during these videos, they are the most important time because that's an opportunity for you to practice and kind of assess, how well do you understand this stuff right now? Because ultimately that's the goal, for you to get to that point where you feel comfortable doing problems like these on your own. So the pauses are the most important time. All right, let's talk about B. So let me start by drawing the graph of y equals x squared, the initial function. Y equals x squared. So what is that 2 going to do to the graph? What is this 2 going to do to the graph? It's going to affect how big my y values are. Essentially, all my y values are going to get doubled. So like if I were to take a look at a point like this on the graph, if I were to double the y value, well, now that y value is, let me put it in a different color, it's twice as high. It's twice as high. And if I double all the y values like that, my parabola is going to get stretched like this. I'm going to say it gets scaled vertically by a factor of 2. Meaning essentially vertically all these y values got doubled. Okay, now let me label the equation. This was y equals 2x squared. All right, let's flip to the next page. So in C, I'm just changing the number that we multiplied by. So that's going to just change how much the graph got scaled. Okay, so if I start off with the graph of y equals x squared, let me just get that down for each of these. Y equals x squared, the original graph. Y equals x squared here. Let's get it down for part E as well. Y equals x squared. So now in part C, well, we're changing the scale. So if I take a look at a point on the graph, now that y value gets multiplied by 1/3. Okay, so that y value is going to get smaller. We're essentially dividing all the y values by 3. If I do that to all the y values, divide them all by 3, well, the graph is it's growing much more slowly than it used to be. So now we are scaling vertically still. Oops, sorry, misspelled that. Still scaling vertically by a factor of 1/3 this time. Scaling it vertically by a factor of 1/3. So this purple graph, this was my y equals 1/3 x squared. Okay, all right, two more of these. In part D, now I'm taking x squared and I'm adding 10. So adding 10, that is going to move the whole graph up by 10 units. So instead of this y-intercept being at the origin, now it's going to be at 10 on the y-axis. So the whole thing got shifted up. So my parabola is looking more like that. That is my graph of y equals x squared plus 10. So this shifts the graph up by 10. Okay, one more to go. So in this last one, we are now looking at x minus 5 squared plus 10. Okay, so what is going to happen with that? We already know what the plus 10 does to the graph. That is moving the graph up 10 units. But what is changing the x squared to an x minus 5 squared? What is that going to do to the graph? It turns out that what that does is, if I focus on the vertex as a reference point, the x minus 5 is going to shift it 5 units to the right. So if I label 5 here on my x-axis, and then from there I got to go 10 units up. Well, if I go 10 units up, am I on the curve, or am I below the curve, or am I above the curve? How do we figure that out? Well, let's plug 5 into y equals x squared. If I plug in 5 into y equals x squared, well, the y value is 25. But if I were to plug 5 into this formula, well, this part becomes 0, and then I get plus 10. So clearly, when I plug it into my new formula, I'm getting something smaller than 25. So my vertex is definitely below this point where the y value is 25. So the new vertex is somewhere here, 5 units to the right, 10 units up. And now if I draw my parabola, it's going to have the same shape, but it just got shifted to the right and up. Okay, so this purple graph, that is my graph of y equals x minus 5 quantity squared plus 10. So here we saw it getting shifted up by 10 and right by 5. Okay, so one of the ways that I can tell that, the vertex, the x coordinate is 5 rather than -5 is, well, when I think about this original formula, the x coordinate of the vertex comes from what makes this part become 0. And I would have to plug in 0 for x to make that part be 0. But in my new formula, what would I have to plug in here to make this be 0? I would have to plug in +5, not -5. And that's one of the ways I can tell this x coordinate is 5. Okay, so one of the key takeaways I want to have from this, specifically from part E, is about how I can kind of recognize that vertex from this formula. So when I get my quadratic into a form like this, maybe I have like a perfect square term, there might be a coefficient in front of the parentheses, perhaps, and then there might be an extra constant at the end. Well, when I have it in that form, h comma k, that point, that is the vertex. So that is going to be the vertex of the parabola. Okay. Alrighty. So, well, if I'm just given an equation of a quadratic, like I am in part A of this next example, how do we get it into a form where we can find the vertex? It turns out we complete the square. Okay, so we saw this method in the previous section when we talked about circles, so we're going to revisit it. All right, so let's take this quadratic, and I'm going to convert it to this vertex form. I'm going to make it look more like that. And once it's in that vertex form, let's graph it and label any intercepts and the vertex. Alrighty, so, well, what's the first thing that I do when I complete the square? I find the coefficient of x, which in this case is -10. So -10. And then I divide that by 2. So that gives me -5. Alrighty, and then I am going to end up squaring that. So I'll draw an arrow, and then I'll put -5. Well, that's going to get squared. And that gives me 25. Okay, So now I add and subtract that number. Okay. This is something that's a little bit different than what we saw with circles. In circles, what we did is we took this number and we added it to both sides of the equation. So I kind of like added 25 here and I added 25 to the other side. I don't want to do that here because I want to keep the y isolated. Okay, so instead, the way I'm going to balance that out is we will write x squared minus 10x, and I'm going to add 25 at the end of these two terms. Still got the plus 16, but to balance out that plus 25, I'm going to put a minus 25. Okay, let me separate out this step over here. Oops. Okay, and now when I do this, well, these three terms should factor as a perfect square. So if I do that, I get y equals, I'll get x, I know it's going to be something squared, and I'll get minus 5. And I could check that. If I were to FOIL this out, I should end up getting x minus 5 squared. Okay, and then on the outside, this 16 minus 25, well, that becomes a minus 9. Alrighty, so now this is in this vertex form where I got this perfect square popping out. So we're ready to write down the vertex. The vertex, we are ready for that. Okay, so the x coordinate of the vertex is what do I plug into here for the x to make that be 0? And that's 5. And when I do plug in 5, what's the y value? Well, if I plug in 5, this part is 0, and then I'll get y equals 0 minus 9, which is negative 9. Okay. All right, so that is my vertex. I'm going to box that. That's part of what the problem wanted. It wanted me to find the vertex. Okay, so now what else do I need to graph it? I need the intercepts. So let's go and get the intercepts. Maybe I'll find the y-intercept first. For the y-intercept, we set our x coordinate equal to 0. Okay, and when I do this, well, I could choose which form I want to plug into. Like, do I want to plug into the original form? Or maybe I want to plug into this form where I'd completed the square. I think it's going to be a little bit easier to plug into the original for this. A little bit less simplifying. So let's do that. I'll get y equals 0 squared minus 10 times 0 plus 16. Okay, and that's just 16. Okay, so my y-intercept as a point, its x-coordinate is 0, and the y-coordinate is 16. So that is my y-intercept. Let's get the x-intercept. So my x-intercept, for my x-intercept, we set the y value equal to 0. Okay, so when I set my y value equal to 0, again, I could do it either in this original equation, or I could do it in the completely the square form. Okay, I could do it in either, but it turns out that if I do it in the completed the square form, it's usually going to be a bit less work. And so let me plug it in there, and then I'll talk about y. So if I plug in 0 for y, I get 0 equals x minus 5 squared minus 9. And I'm going to try to isolate the x. So let's move the 9 over. 9 equals x minus 5 getting squared. And now I can square root both sides. And that'll give me x minus 5 on this side. On the other side, I get 3. But if I square root both sides of an equation, I got to put a plus or minus. Okay, so the nice part about having this thing in my completed the square form is, well, we didn't need to FOIL this whole thing out. Because it was a perfect square, I could just isolate it and then take the root to get rid of it. That's really nice. That's one of the things that makes completing the square very nice for algebra. Okay, so we have these two cases. Let's solve each of them. So either I'm getting x minus 5 equals 3, or x minus 5 is negative 3. In both of these, I'll add 5 to the other side. So here I get x equals 8. And the other one, if I add 5, I get x is 2. So my x-intercepts, there's 2 of them. I'm getting 8, 0, because remember the y value is 0 at the x-intercept. And we are also getting 2, 0. All right, so let's box these. Okay, let me briefly just talk about what would have happened if we had plugged in y equals 0 into the original equation, because we also could have done that. If I'd plugged it into the original, we would have gotten 0 equals x squared minus 10x plus 16. Okay, and I have a quadratic equation. I'm trying to solve it. So typically the first thing that I would try is I would try to factor it. This one's kind of nice because it factors very nicely. So I'll get an x, I'll get an x. I need two numbers that multiply to 16 and they add to negative 10. So that's going to be negative 2 and then minus 8. And now that it's factored and it equals 0, from the first parentheses I get x equals 2. From the second one I get x equals 8. So I'm getting the same answers that I got here. And you might be wondering, wait, this kind of seemed faster than what we did here with completing the square and doing it that way. So why? Why did I do it this way? Well, the short answer to that is that this one maybe is especially nice and a little bit easier in that this quadratic factored. But if it didn't factor, as is often the case, then to solve this way, I would have needed to do quadratic formula. And that's typically going to be a lot more algebra and simplifying than doing it this way. Okay, that's just something to keep in mind. That's why that's why I did it in the completed the square form. All right, so I got my vertex, got my intercepts. It wanted me to graph the parabola. Let's do that now. So let me draw my axes. Y-axis, x-axis. Let's see, my vertex is at 5, 9. Or sorry, negative 9. 5, negative 9. That's somewhere down here. 5, negative 9. The x-intercepts, there's one at 2, 0, and there's one at 8, 0. I'm just going to start to draw the shape of the graph already. I can tell already at this point that it's going to be an upward facing parabola. And then this way as well. Okay, and then where it crossed, I'm going to label that as my y-intercept. So that was 0, 16. 0, 16. So my picture is totally not to scale, but nonetheless, I have all of these relevant points labeled. Okay. Alrighty. So let's take a look at another example, but let's up the difficulty now this time. Let us up the difficulty. So the next one, I got a 1/3 x squared plus 6x plus 50. So I want to do the same thing for this. I want to get it in vertex form, graph it by finding those intercepts and the vertex. Okay, so it turns out that when the leading coefficient is the thing in front of the biggest power term, that is the 1/3, that's the leading coefficient. When that number is not just 1, there's an extra step when I complete the square, which is I need to factor it out of just the first 2 terms. Okay, so let's do that. So I could rewrite f of x as just y. And if I factor out the 1/3, I'm just going to factor out the first 2 terms. I'm going to leave the plus 50 outside. The reason for that is the plus 50, this constant term at the end, that part doesn't really impact when I complete the square and I try to figure out what number to add to this. Like even for the previous problem, the 16 wasn't so important in coming up with this number, the 25, that I needed to make the perfect square. So just like here where I kind of left the 16 at the end, I'm doing the same thing here with the 50. Okay, well let's factor out a 1/3 out of these 2 terms. So from the first term, that's easier. I'm just left with x squared. But what's left over from this 6x? Well, the way I can do it is, what I'm going to be left over with is the thing that's currently there, which is plus 6x, and you divide it by what you just factored out, which is 1/3. And if I wanted to check this, I could take the 1/3, I could distribute it back, so times the x squared, that gives me this thing. And then if I distribute into this, well, it would cancel with my denominator, and it would just leave me with that 6x on the top. So it will give me the same thing as what I had before. Okay. All right, so let's simplify now. The thing inside of the parentheses, well, I get x squared. And then if I divide 6x by 1/3, dividing by a fraction is the same thing as multiplying by the reciprocal, which is 3. 6x times 3, that's 18. 18x. Okay, so what we got is y equals 1/3 parentheses x squared plus 18x. I'm going to leave some space now in the parentheses. Okay, because now the thing in the parentheses looks a whole lot easier. I don't have that leading coefficient anymore. So now I'm ready to complete the square and do that whole divided by 2 thing. So I'll take the coefficient of x, which is 18. I will divide it by 2 to get 9. And then I square that number. So 9 squared equals 81. Okay, so I add 81 and I subtract 81. I need to do both of those inside the parentheses. Add 81 and subtract 81. Both of them have to be inside of the parentheses. That's really important. If I were to try to put the minus 81 outside, why is that wrong? The reason why that's wrong is the one that's inside the parentheses is getting multiplied by 1/3. So 1/3 times 81 that's actually plus 27. So I'd be adding 27 there, but then subtracting 81. But overall, that's changing the value. Like, only when I add and subtract the exact same number does it end up just being plus 0, and that wouldn't change it. So I can't put the minus 81 outside the parentheses. That's the key takeaway. Otherwise, I haven't actually added and subtracted the same value. Okay, so let's put that minus 81 back inside. And now when I do this, these first 3 terms should factor as a perfect square. Okay, so y equals 1/3, parentheses, parentheses. And now those first 3 terms should factor as a perfect square. And I'll still have my minus 81 outside of it. Okay, so I know there's going to be an x. And then what number goes next to it? You might already see it, but I'm going to talk about a shortcut for how I could figure out what that number is. The shortcut is the number that goes there. Let me actually write the number first. It turns out it's plus 9. The number that goes there to make that factoring work, it's always going to be what I got when I did the whole, coefficient of x and I divided it by 2. Like when I divided it by 2, I got 9. It should always end up matching that. Like even if I go back to my last example, when I divided that coefficient of x by 2, I got -5. And notice that's what number ended up going in that perfect square part. That should always match up, and if it doesn't, I did something wrong. Okay. All right, cool. And then, of course, I got that plus 50 at the very end. All right, so now what I'm going to do, I can simplify this a little bit further. I got this 1/3 in front. Let's distribute it to the perfect square and then distribute it to that -81. So that's going to give me y equals 1/3 is going to multiply the perfect square, x plus 9 squared. I'll just leave it in front. And then I'll get, well, it's a positive 1/3 times a -81 plus 50. Okay, let's simplify the stuff at the end. 1/3 times -81 is -27. And then I got plus 50. And then I could add those terms. So that gives me y equals 1/3 times x plus 9 squared. And that is plus 23. So now I got it in my vertex form. I have this perfect square. We're allowed to have a coefficient in front of it. And then we could have a constant at the end, adding or subtracting. So let's write down the vertex. So the x-coordinate is what I plug in here to make the perfect square be 0. And that's -9. And if I plug -9 in for the x, well, this part becomes 0. So that means y equals 0 plus 23, which is just 23. That's my vertex. That is my vertex. So before I find the intercepts, what does this number, we call this value a. Right, in my general formula, this coefficient in front of the whole parentheses we called it a. What does that a tell me? So this tells me whether my parabola is upwards facing or downwards facing. Because when this number is positive, we have an upward facing parabola. But if this was a negative number, and we'll see an example of that later, it's downward facing. Okay, let's get those intercepts. So let's get the y-intercept. To get the y-intercept, I plug in 0 for x. And I could either do that in the completely the square form or in the original. I think plugging 0 is going to be a little easier in the original. So let's do that. Y equals 1/3 times 0 squared plus 6 times 0 plus 50. Okay, and that's just 50. So my y-intercept is 0, 50. All right, I'm going to box that. Sorry, parentheses, 0, 50. Let's do the x-intercepts. X-intercepts. Now I plug in 0 for the y. And just like I did in the last example, it's going to be a little bit easier algebra-wise to plug that in here in the completely the square form. So I'll plug 0 in for the y. 0 equals 1/3 times x plus 9 squared plus 23. And this one for sure, it's going to be easier in this form, because if I try to plug it into the original, I could do it, but it's going to involve quadratic formula to solve. It doesn't factor. It doesn't factor so nice. Okay, so how do I solve this? Well, let's isolate the square. Let's move the 23 over. So that'll give me negative 23 equals 1/3 times x plus 9 getting squared. So at this point, I can actually see what the answer is without doing any more work. Give this thing a quick pause for about 30 seconds. See if you can identify what the answer is without really doing any work at all. 4, 3, 2, 1. Pause it just for 30 seconds. See if you can figure that out. All right, let's bring it back together. Let's talk about it. So it turns out this thing has no solution. Why is that? Well, on this side, I'm squaring something, and then I'm multiplying by 1/3. So overall, that whole thing has to be non-negative. There's no way it can equal a negative number, so I'll put a slash through this. That's how I can tell there's going to be no solution. I could have gotten the same thing if I, multiplied the 3 over to the other side, and then I square rooted both sides. I would have ended up square rooting a negative number, and that's undefined. But this is just a bit quicker. So try to find x-intercepts. I wasn't able to get any because I got no solution. That means there are no x-intercepts. Okay, so no x-intercepts. Interesting. So if I go to draw my graph now, let me draw my axes. Let's draw our axes. So our vertex is at negative 9, comma 23. That's somewhere here in quadrant 2. I know because this coefficient in front, the a was positive, it's upward facing. So I'm going to draw an upward facing quadratic. And I can tell just from the graph even that clearly there's not going to be any x-intercepts. So the algebra that we did checks out. I like that. Let's label the y-intercept. I know it's 0, 50. And there we have it. There we have our graph.